Last time we had taken a look at section 7.4, we had talked about percents, and we had gotten to the point where we were just introducing interest. And so let me start with this interest slide where we had defined a number of terms. We had talked about interest being the money that we make or end up owing extra when we either put money in a bank or borrow money from a bank. Principal being the amount of money we originally either put in there or borrow. Our interest rate is the percent that we use to determine what the interest is going to be. It's usually given in percent form, and we have to turn it into a decimal in order to use that value. Simple interest is the kind of interest that is often calculated when you borrow money from from an individual person, like your parents or something like that, and they're supposed to be trying to teach you something about how borrowing costs you, kind of thing. And then compound interest is the type of interest that's typically used at a lending institution like a bank. The benefit and sort of the flip side, both positively and negatively, of compound interest is that you owe the interest based on how much you currently have owed to that company, or how much you currently have sort of in deposit with that company. So the more you have that you owe, or the more that you have on deposit, the more the interest rate's going to be. And then as you make withdrawals or deposits or payments or whatever, the interest rate fluctuates based on what's currently in that account or owed to that account. So that's what compound interest does. And I talked about the fact that in your book they use a different formula for the compound interest. I am going to use this one because this one is the most commonly used sort of across the board. Yes?
Is simple interest the one where interest stays the same, like when you borrow this much money, the interest is
Exactly. Yeah, so if you borrowed the money every month, the payment amount would have $50 of interest. Exactly the same thing every time. So yes, that is the way simple interest would work. Whereas on a compound interest, what happens is that, in fact, if you have a loan or a savings account or something like that with your bank, you'll notice that the interest either that you're paying or you're receiving fluctuates from month to month, or from sometimes quarter to quarter, depending on how it's being accrued. And so sometimes when you make that payment, your interest rate's higher than other times because it's being calculated on what you currently have owed on that product, or what you currently have on deposit with the bank. Yeah. All right, so we're going to do an example 9. Oops. All right, a company is expanding its line to include more products. In order to do that, it needs to borrow money, $320,000. It's being borrowed at 13.5% annual simple interest. And the key words are there. If you look for them, it will tell you in a problem. You don't have to sit here and think, is this like borrowing money from my mom, or is this like borrowing money from the bank? It's in the problem. It will tell you. Okay, so this says simple interest. That tells you which formula to use. And it says it's for a period of 18 months. How much interest must the company pay? So we need the simple interest formula. So what is the simple interest formula that we just used on the other slide? I'll start with A equals. What's it say next?
P plus PRT.
Yep, P plus PRT. There's another form of it. It was P times 1 plus RT. It's identical. It's just calculated with multiplication instead of addition of the two things. In particular, if you take a look, this is the principal. Is it LE or AL? I can never remember. AL on this one? Okay. And then this right here is actually the interest. So for the purposes of this particular problem, we really only need to calculate the PRT part. Now you can't do that with compound interest. We don't have a way of separating it out. But for simple interest, this piece PRT is actually the interest part of it. So we could actually use sort of an abbreviated formula for simple interest where it says I equals PRT. So we'll go with that this time around. What is P? It's the original amount. So in our problem here, that's the $320,000. R, interest rate, what's that going to be? Yeah, it's 13.5%, which I need to write as a decimal value instead. What will that look like? Right, 0.135. And then T stands for time in years, and that's really important, years. How many years are they going to have to pay this money back? 1.5, 1.5. And then it's a matter of grabbing your calculator and multiplying out what the final result would be of this borrowing decision. 320,000 times 0.135 times 1.5. I'll put a dollar sign because it's money. Ellen, do you have an answer?
Yeah, 64,800.
Do I have a second? Someone else find that value, same thing? Yep, okay, I got a couple nods. All right, so $64,800 is the interest that they will be paying for the luxury of having borrowed that much money. Okay, so when they pay the money back, they owe the $320,000 they borrowed. Plus they owe $64,800 more. So this is the additional amount of money that they have to pay back to their lender. Are you following? Okay, so that's the first one. The next one, we're going to compare 3 different investments. Johnny and Carolyn have 3 savings plans, which accumulate to the following interest for a 1-year time period. First one, a passbook account made $53.90 for a principal of $980. The CD made $55.20 on a principal of $600. And a money market made $158.40 on a principal of $1,200. The question is, which account paid the best annual interest rate for 1 year? Now, while this one talks about interest rates, it's really a question that involves proportions, okay? And the reason it is because they're doing it for a fixed 1-year time period, and what they're really asking us for is what percent this is giving us, right? I mean, an interest rate is just a percentage. So this is like the problems we were dealing with last time. So we're going to set up proportions for each of these. So on problem number 1, it tells us that the amount that they made was $53.90. So that will go in my numerator. And the amount that they had on deposit invested was $980. And what we want to know is we want to know what percentage this is out of 100%, right? I'll leave that off. I've already got it set up there. So what do? Yeah, we just cross multiply. You're going to cross multiply. And what are you going to get? What was it? 5.5, and that is a percent, because this was the number per 100 that we started out with. So the first account was 5.5%. Account number 2. How will I set this one up? Same exact way, you bet. 5520 over 600 equals x over 100. And we shall cross multiply. So 5520 times 100, and then divide by 600, right? What's that one give me? 9.2%. That's better, isn't it? You betcha.
So does the 100 go on the same as the principal because those are both like the 4 value?
It's the first amount of the investment, exactly. Yeah. So I'm kind of, and I didn't write it down, but it probably wouldn't be a bad idea that this is our initial amount, and this is our increased value. In this case, it's interest. How much we're making. Yep. All right, last account. 1, 2, 3. I have $158.40 on a $1,200 investment. And again, can cross multiply. $13.2%. So which account paid the best interest rate? Yeah, the third account. So the answer is the money market. And this is the work that supports those different features. Make sense?
So we're trying to find out how much the company made, not what they were charging.
This one is one where they made money. These amounts are the amounts of money that it's not a company, but this couple, Johnny and Carolyn, it's how much money they made in their investments. So it's like they have 3 basically savings accounts, and they get interest in all 3 of those accounts, and they're comparing after the fact the interest amount that they got compared to the amount of money they had on deposit at that location. Yeah. All right. We're going to try another one. It doesn't look exactly like an interest problem, but it works just like an interest problem, so we'll talk through it and see how that makes sense in a second here. All right, the question says, a publishing company signs an agreement to allow a textbook with a first edition, 500 pages, to expand over several editions until it gets to 1,000 pages. And the book is growing at approximately 10% in the number of pages over each edition. Okay, so first textbook's 500 pages, the next one's going to be 10% bigger. That's what that's saying. The question is, how many editions can they publish before they reach the 1,000 page limit and they are no longer in contract? Okay, so the first edition is 500 pages for sure, right? What do I do to find out how big my second edition is?
I would multiply it by 0.1 and then add it.
So you would do something like this. Does this look right, Shelby? So you take the original 500 plus 500 times the 10%. This works. This is a little bit, this is one of the ways to do it. There's another way I'm going to show you in a minute. This will work. Yeah? What does this give me for my second edition? $550 pages. And that should make sense, right? 10% of 500 should be 50, so this is 550 pages. So what am I going to do for my third edition? 550, that's the new book, the previous edition. And I can do the same thing. I can do 550 times 0.1. I'm going to show you a couple of ways to do this after this too. There's at least 3 ways on the top of my mind that I can think of. This is definitely one of them. All right, so 550 plus 550 times 0.1. What's that going to give me for the third edition? 605? Okay, so how many steps am I going to go? When do I know I'm finished with this process? I'm going to keep going through this process. When will I be done? When I get to 1,000 or more than 1,000, in which case I can't print the book, right? Okay, so let's keep going. Fourth edition. What will I do? 605, plus 605 times 0.1. What does that give me? Okay, so we're going to round a whole number of pages for the moment and that's a terrible number to put there, but that's okay. We are going to just round a whole number of pages. We recognize that in the end, our answer is probably not going to be close enough to exactly 1,000 that it's going to affect our answer. Our answer is really not about the page number. It's about exceeding the page number 1,000, right? Does that make sense? So we're going to round as we go. Fifth edition. Now I have that 666 plus 666 times 0.1. Okay, one at a time. 730, so 733. Okay, 733. Sixth edition, 733 plus 733 times 0.1. This may be the first time I've written it out this way ever. It works pretty well though. You guys seem to understand what's going on here, right? 10% more than the last one, right? What's this one going to give you? 806. Seventh edition. 806 plus 806 times 0.1. If you're wondering when are we ever going to be finished, it's very soon. We're getting close. What's this one? 887. Will we get another book? 887 plus 887 times 0.1. I'm going to guess that's our last book. What do you think? Probably so. We can double check by taking one more book to try for. A 9th edition, 976 plus 976 times 0.1, and we'll end up with what for our page number?
1074.
And that one's too large, right? Okay, so this is a perfectly reasonable way of doing this particular problem, and it really actually didn't take us all that long to do it. I mean, we had several iterations of it, but it's not that bad. So the question is, how many editions could be published? And the answer would be 8 editions, right? All right, so I'm going to take what you guys have already done here, and I'm going to change it just a little bit to show you that you can think about this in a very slightly different way, and at least the entry into your calculator will be a little bit quicker. And then I'm going to show you a completely different approach to how you're thinking about it as well. So let me move this over. What I'd like for you to notice is that every single time that I wrote these values down, I wrote the number twice. Do you see that? So what's going on here? Well, this is like doing simple interest. So over here on the simple interest formula, I had 2 formulas here that are exactly the same, right? And do you notice that in the first version of the formula, I have the p listed twice? And the second of the version of the formula, I only have it listed once because I've written it sort of as a multiplication factor. So what we could do over here is we could recognize it from that perspective. In other words, right here, what I could have done is I could have said that I'm going to take the 550 pages and multiply that by 1.1. Why 1.1? Where's that coming from? The 1 represents the first number, 1 times that value, and the 0.1 represents the 0.1 times that value. Another way you can think of it is that 1.1 would be 110%. Well, that's exactly what I have. I have a book that's 110% of what it originally was. This would save you keystrokes in your calculator if you recognized it. We're not talking like huge amount of difference of time, but it might cut your time in about a third or a half of what you were using before. Okay? So, and you could do that on each step, right? So this step would then be the 550. I'm a step ahead. 550 times 1.1. You'd have 605 times 1.1 and so forth all the way down. Okay, so that's kind of a neat little, mathematical trick. It almost feels like a little bit to shorten up what we're doing.
Is the first one supposed to be 500?
The first edition was 500, right here. And then the second edition was I see what you're saying. Right here was my 500. You're right. Thank you. Yep. Okay. But let's think for a moment. We've sort of thought through this like it's simple interest, except that it changes every edition, right? So it's not really simple interest. This problem is actually a lot more like compound interest. Compound interest means that the next edition, in this case, the next edition is based on the previous edition's size. Well, that's what compound interest does. The amount of your interest is based on the current size of your bank account or the current size of the loan that you have outstanding. So what could we do? Well, we could actually set this up like the compound interest formula. So the compound interest formula looks like this. Now, the letters don't exactly represent the same thing because we're really not talking money here. We're talking about pages in a book. So we're going to have to think through how it relates to the idea of pages in a book. Well, P still is the amount you originally put into an investment. Well, P would be the amount of the pages of the original textbook. So that's 500. 1 is our number. R is our interest rate. That's 0.1, right? It's the percent that the book is increasing by every year, or increasing by every edition in this case. N normally represents how many times per year something's happening. Well, this isn't happening per year. It's happening for every edition of the book, right? So in every edition of the book, we increase it by 10%. Well, that's per one edition made. So N is actually like the number 1. And we can actually represent that N as 1 up here too. And the T is what's changing. T in this case is not time, because that's not what's actually increasing. It's increasing by edition number. So in our problem right here, this T is the edition number of the textbook that we're on. Sort of. Or almost. It's close. So this formula actually becomes 100 times 1.1. Do you recognize that 1.1? It's that 110% to the power t. And the power t should be the addition you're on, like I said, sort of. It's actually not quite the addition you're on, because if you plug in the number 1 here, what do you get? You get 550, which is not your first addition, it's actually your second addition. You're off by 1, right? So the addition itself, the t here is actually is off by the addition number. So it's the I don't know how I exactly want to write it. I know what I do. Let's do this. Let's use that formula, and we'll do. Whoops. And we'll do an example. So let's say that we want to find out the fourth addition. You know what? Actually, even better. Let me do it this way. Let's do it one by one for the additions that you've actually got over here. So go ahead and grab your calculator, and I want you to write in 500, parenthesis 1.1, and then the caret key. Now, this works for those of you who have the, it might work for the scientific ones as well. Do you have the ability to do it in multiple steps all at the same time with parentheses, those of you who have scientific calculators? I see a lot of TI-83s. I know you guys do. Okay, so if you want the first addition, what is your t-value? That's actually the t-value of 0. So if you put in a t-value of 0, you get the first edition of the book that you're working with. What if you put in the second edition? Well, you're going to have to put in t equal 1, right? So it's not 2, it's actually t equal to 1. And you get 550? Yeah. So let's trace down here. We'll do one more. T equal to 2 for the third edition. When you put in t equal to 2, do you get 605? Excellent. Down here, let's try this one. What if I wanted the 8th edition? What would that look like? T equal to 7, right? It's 1 less. What if you plug in t equal to 7? It's not going to be exact because we rounded our approximations before, but it's pretty close. What do you get? 974. Okay? And remember, the question didn't ask us about page numbers. The question asked us about additions. So what happens if you put in t equal to 8? You get something bigger than 1,000, right? So those are 3 very different ways of doing the problem. Not very different, but they're 3 different ways of doing the problem depending on how you see it and how long it takes you or how long you want to take to manipulate through the processes. Okay. All right, I have one more example for us. Again, this one doesn't quite look like an interest problem, but it works the same way interest problems do because we're doing something at a percentage multiple times. Because of a recession in the value of a new house, it depreciated 10% each year for each of 3 years in a row. Then, over the next 3 years, it increased by 10% each year. Did the value of the house increase, decrease, or stay the same in 6 years? So at face value, this looks like, well, it went down 10% 3 times, up 10% 3 times, and so your natural inclination might be to say what? It stayed the same. I mean, that sort of seems like what we would do if we were adding and subtracting these values. But you have to remember, we don't add and subtract percentages. What do we do with them? We use multiplication. So what we're going to do is we're going to explore whether or not we really did increase or decrease or stay the same in the price of the house. Now there's a catch to that. What is it? Well, it is compounded. We're going to have to deal with that. Thank you, Devin. We do not know a price of the house. It doesn't tell us how much the house cost, right? The reality is it really doesn't matter how much the house cost. Whatever the house cost, it's increasing and decreasing by some percentage, right? This is kind of like what happens when I hear it sometimes. I heard it a lot when I was younger. People say something like, I don't make enough money to tithe. Well, it's 10% of whatever you make. My 10% is going to be more than your 10% because I make more. So maybe I have more of an issue to say I don't make enough because I have to pay more now. It's 10%. So it doesn't matter how much it is, it's going to be affected in the same way because it's a percent change. You know what that means? We get to pick the amount of the house price that we want to work with. So we're going to pick something that's going to be nice and convenient, or at least as nice and convenient as possible to work with. I'm going to pick $100,000 for the price of the house. Okay, it's a reasonable house price for one, and then also it's a nice, round, pretty number. Okay, so we're going to initially say that we have our starting price for our house of $100,000, and we'll talk about in the end how to sort of back out of the fact that I made up a number for the price. Okay. But for starters, it doesn't really affect much. This one does say that I'm going to depreciate the value of the house by 10%. So what does that mean? It goes down, right? It goes down in value by 10%. So one way to do this would be to find 10% and subtract it, kind of like we found the 10% and added on the last problem. But also, I showed you this nice way, and it wasn't too terribly different, of calculating it directly without having to do the addition. So I'd like to do this problem that way. If I had 100% of the price of the house and I lost 10% of the price of the house, how much is the house worth from before? 90%. So we're going to go with 90%. So after the first year, we're going to have that same $100,000 times only 0.9. It's only worth 90% of what it was the previous year. What would that be for this value of our house? $90,000. Year 2. I don't have a $100,000 house anymore. I have a $90,000 house. Right? Yeah. And then I have to do the same thing again. It's going to depreciate again, according to the problem, by 10%. What's that going to give me? $81,000. You can just watch the money just sliding all out of the checking account right there, can't you? Year 3, because it says it's going to happen for 3 years, I got to do it again. $81,000 house now. 90%. The percentage is going down. It says it decreases by 10% per year. Right. Now the amount is going down. Notice the first time it went down $10,000, and the second time it only went down $9,000. So the price, the amount that I'm losing every year is different, but the percentage isn't. All right. So what do I get for my 81,000 times 0.9? 72,900. Okay. And thankfully, something happens that's an upswing after that, and it says the market sort of turns around, right? It increases now by 10%. So what am I going to have to change in order to take care of year 4? Yeah, I'm going to take that $72,900 house, and I'm going to multiply it by 1.1. Okay, why 1.1? The original price plus the extra 10%. Or you can look at that and you can recognize 1.1 means 110%. Right? So the original 100% and 10% more. So what happens when we take 72,900 times 1.1? 80,190. Good. Year 5. All right, I've got my 80,190 times what? 1.1. Good. And this will be our last step, year 6, because it only talked about doing it in 6 years. So now I have an 88,209. And it's going to go up one more time by 10%. to leave me with what? Yeah, we can round off to the whole dollar. That'll work. So $97,030. Okay, so the first question that we're going to answer then is, did the value of the house increase or decrease in 6 years? It decreased, right? Now, you cannot say it decreased by $2,970. Why not? Yeah, we made up that $100,000 house, right? So if we had a $100,000 house, it would have decreased by that amount. That's okay. But it would actually be a lot more helpful if we could talk about what percentage it decreased by. So how could we find out what percentage this house decreased by? Set up a proportion. All right, so what's my proportion setup going to look like? All right, so 97,030 over 100,000. X over 100. So you tell me what you get when you get there. $97.03. Now, this is a percentage.
I thought, since you did that,
So it decreased 30.
Okay, sorry. There's like 4 of you who are all looking at different things a little bit differently, so let me take one of you at a time. So Rachel, what are you saying?
I said it decreased by 30. That's like the original, or that's how much of the original 100,000 that you're paying. So it decreased by 3%.
Okay, so if we do the problem this way, what would we have to do next?
Subtract
From 100. Okay, so because this is how we set it up at this point, we would want to take this and subtract it from 100. And I mean, we can do it to the decimals that we have since we've got them. You could also just roughly round this and say it's about 3%. I mean, we're looking at a roughly 3% decrease in price, right? So this decreased by about 3%. If we'd been a little bit more careful in the setup of the problem, what could we have done with that proportion that would have looked different? Yeah, we could have right here have written the amount that we actually lost in value of the house instead. And if we'd done that, then the percentage that we got at the end actually would be the 3% roughly that we are sort of, you know, in a backwards way kind of coming around to. Does that make sense? Okay. Now, this is actually compound interest. If you actually take a look at what we did right here, this was taking 100,000, I'm sorry, too many, not enough zeros, 100,000. It was times 0.9 to the t, and we did it 1, 2, 3 times. Because we did it, you know, it changed every single time. That's what actually what Amanda was saying was that isn't the percentage changing. And I said, no, not the percentage, but the amount is changing by which we were subtracting every time. And then down here, we took the original amount, which was our 80,000, I'm sorry, our 72,900, and we multiplied it by 1.1 to the t. And we did it 1, 2, 3 times. We didn't do it up to 6 because 6 years actually was the 6 years total, not the 6 years of the increase. So that's actually a compound quantity as well. But if we do it in iterative, like do it one after another, this is a recursive relationship, then you don't really see that happening, but it is actually, that's exactly what's going on. Any questions on that one? All right.